Multiple testing. Hello student, today I am going to demonstrate one case study on multiple testings as a part of postdoc ANOVA. So to demonstrate this particular topic, I am going to take a data. The data is about a baby's birth weight and related to the mother's smoking status. So there are 4 different smoking status and the baby's birth weights that are collected in the data. So initially I will feed the data in ANOVA model, and from that I will explore the different type of multiple comparison test, and I will compare their respective merits and demerits. Those tests are one the Bonferroni adjustment, the Holm adjustment, Fisher's least significance difference method, the Tukey's honestly significance difference method, and the Scheffe's method, Duncan's method, and few other alternatives that I will talk about in this module, and the related R functions that are available from different type of packages that you need to use while you analyze those data by those respective models. And then finally I will conclude the results and interpret based on whatever we get as a output of those functions. So from this module, I am expecting that if you go through this module, you would be able to choose appropriate methods for multiple comparisons and the respective functions that is required to test in R. Let's focus on the data. When researchers studied the association between birth weight of babies and mother smoking habits, that group 1 consists of the non-smokers, group 2 comprises smokers who smoke less than 1 pack of cigarettes per day, group 3 smoked more than 1 but fewer than 2 packs per day, and group 4 smoked more than 2 packs per day. So there are 4 groups, and this is the data looks like. There is group 1, group 2, group 3 and group 4. So total n equals to 11. It's a balanced design, and the main question is from this: what do you conclude about the effect of smoking on mother's weight? So this is the data that I am going to use for different multiple testings that I explored. Before that, as you know, you have to fit a ANOVA. So before putting ANOVA, I will generate few very basic descriptives to just have a look about the distribution of the data to see whether that's satisfying the assumptions of ANOVA or not. Not in details, but just a very preliminary thing. So now what you have to do, the data is in a tabular form that need to be entered in R. Either you can enter in a text file and import in R, or you can directly enter in R. So here I enter directly in R console. So I create the variable BW1 as the birth weight of the group 1, then BW2 as the birth weight of the group 2, and BW3 is the birth weight for group 3, and 4 is the group 4. And as you know, the data should be entered within function C. C stands for column, and then finally data can be formed in this manner: data equals to data dot frame serial number 1 to 44, because each group had 11 participants. So 11 into 4, that is 44. So 1 to 44, and the birth weight equals to this. So the data has formed, and then you have to create one more variable that is called group, that I use the replicate command to create this group. It's very simple. I am not going in details, but if you need any clarity, you just question mark rep you enter, then you will get the details how to use the replicate function. So just have a look of the data that I created, it should be in this form. It should looks like this. So first column is the serial number, the second column is the birth weight, and then group indicates the which groups the birth weights belong. So as I told, I'll generate few basic descriptives. To generate the descriptives, I'll call the epicalc package and the function sum, that function I'll use, and use data. That function is used to attach the data. So it attaches the data, so directly you can access the columns of the data frame. So here I generated the summary of birth weights stratified by different group. So this mean, median are not that much difference, so it seems data is quite. So let's fit the ANOVA model. For fitting ANOVA model, I'll use the function called let's say linear LM function is actually is for linear model, that is the linear regression. So initially I will consider this as a simple linear regression, birth weight as the response and group is the predictor. So I'll feed the linear regression model, and then that object I'll pass through the ANOVA, and if this ANOVA, once you pass, that will generate a ANOVA table. The ANOVA table indicates that this p-value is, this is the degrees of freedom, sum of square, mean square, f value, and the p-value. The p-value indicating it is much lower than 0.05, so it is statistically significant that the birth weight varies across different smoking status of mother. So as it is significant, as you know, we really need to identify whether all of the groups are responsible for this difference, or few of them are responsible and few are not. So for that, as we know, that we need to go for pair comparison, that is called post-hoc ANOVA test. So my main objective here is to see what are the different alternative tests exist to do a post-hoc ANOVA test. So hypothesis that we test here, H naught mu1 equals to mu2 equals to mu3 equals to mu4, and the p-value is less than 0.05. So it is statistically significant, as I mentioned. So now we'll proceed to the different post-hoc test. First we'll start with the Bonferroni correction. The Bonferroni correction is very simple correction where the total probability of type 1 error, that is 0.05, is considered to be the family error, and then it is equally distributed to the number of tests that we need to do. That means the number of pairs that we need to compare. So in a minute I can explain. So, but to do the Bonferroni corrections, I will use that function pairwise .t.test. This function you can use where you just pass the birth weight and then the group, and p adjust equals to Bonferroni. Bonferroni here, B in F is stand for Bonferroni. For other alternatives, you just take the help of pairwise.t.test or the question mark pairwise.t.test. That will give you much more details about what are the alternative adjusted options are available, and that will generate this particular table. This one matrix, the lower triangular matrix given, it is the adjusted p-value. If you see, group 2 and group 1 are statistically significant, group 1 and group 3 are statistically significant. It seems all the groups are responsible for this significance. So that means the birth weight actually varies across all the groups. So they are statistically different for all the groups, as all the p-values are less than 0.05. This is, remember, this is the adjusted p-value. It is not the original p-value. It is adjusted, Bonferroni adjusted p-value. So you can check with respect to the simple p-value criteria, as p should be 0.05 for statistical significance. So as I mentioned, that the Bonferroni adjustment simply divide the type 1 error rate by the number of tests that you are going to perform, in this case 4. So it would be 0.05 by 4. That would be the required type 1 error for each test. But remember, this is not, you don't need to check with that value, because this is adjusted p-value. but hence we divide equally for all the number of tests that you are going to perform. This method is often considered overly conservative. And if you just want to compare the mean, you can just for your comparison, I just put the mean for different groups, mean birth weight for different groups. They are statistically significantly different. Next, I look for the Holm adjustment. So the Holm adjustment sequentially compare the lowest p-value with a type 1 error rate that is reduced for each consecutive test. Just I just work out here in our case. Suppose in the first test the p-value, the adjusted p-value would be the probability type 1 error of the first test would be 0.05 by 4. There are 4 groups, so 0.05 by 4, that is 0.0125, and the second at 0.05 by 3, then this is 0.13. The third test it is 0.05 by 2, that is 0.025, and at the fourth it is 0.05. So this method is generally considered superior to the Bonferroni adjustment. Again, to perform this adjustment for a multiple comparisons, that is the type 1 error adjustment, the same function pairwise dot t dot test, and same way, just the change would be p dot adjust value, that is here instead of BONF, I will put it HOLM Holm adjustment. That will generate the same kind of results. Here I just put the mean over here just for your comparison, and that also indicates that all the groups are pairwise significant. So pairwise comparison indicates all the pairs are statistically significant. They are significantly different from each other. Least significant difference method introduced by Fisher. So this method essentially does not correct the type 1 error rate for multiple comparisons and is generally not recommended relative to the other comparison. However, it should be if somebody wants to perform that LSD test, I mean that function can be called from Agricoli package. That package has to be installed and load, then you will get the function lsd.test. But in recent tests, these the required arguments are not required, and recent tests also help you to if you just want to combine the LSD with Bonferroni corrections or any type of corrections, that can be done with this function. I'll show in a minute, and show this and if you want to use the old method, that also will accepted by this function, then this DF error and the MS error can be found in the ANOVA table. So let's see how I am going to perform it. So as I told, the library Agricoli needs to be installed and load in the R console, and then I'll use this AOV command here, that for ANOVA and birth weight and group simple these things, and then this object, I'll create this object. This is the ANOVA object. That ANOVA object will pass within lsd.test function and groups, then p adjusted Bonferroni correction. This is much more only simple LSD. This is much robust than the simple LSD. So I'll do a Bonferroni correction here, and you should mention console equals to true, otherwise it won't show you the output. So if you put console equals to false, it will run without showing anything unless you put it is true. So it will display the results in the console, and then if you see this, the results will be given in this fashion, and this is the 95% confidence interval of the mean, and actually you need the last table, which is this table. Just have a look. Means with same letter are not significantly different. That means when you are comparing the mean between group 1 and group 2, if these two letters, so this table is just carefully compare if A and B, the group 1 and group 2, the groups A, B, this is mentioned. If any letter common between these two, it is only 2 letters, so there is no common, that means they are significant. when for group 1 and group 3 A and C, so there is no letter common, that means they are significant. That means all 4 letters are distinct and different, so all the 4 groups are significantly different, as we saw earlier. So next we'll focus on the Scheffe's method, and the Scheffe's procedure, perhaps the most popular of the post-hoc procedures, the most flexible and most conservative. The Scheffe's procedure corrects alpha for all pairwise or simple comparisons of means, but also all complex comparison of means as well. So Scheffe's, that's why Scheffe is the most popular method. The complex comparison involves the contrast of more than 2 means at a time. As a result, the Scheffe's is also least statistically powerful procedure, but it should be recognized that Scheffe's is a poor choice of procedures unless complex comparisons are being made. To perform the Scheffe's method, we can use the Scheffe's.test function from the same library, that Agricoli, and there you just put that ANOVA object that I created with the name model, then group is true, and then console is true, and that will generate the results for Scheffe's test. The results should be as is, it was there in the LSD test, and you should focus on the last group, last table, that is A, B, C, D. That means all 4 letters are distinct, they are different, so that means all the groups are significantly different. All the all pair comparisons are significantly different. The another test is the Tukey HSD test. This is one of the most widely used test, is the Tukey HSD test, and Tukey test was developed in reaction to the LSD test, and studies have shown the procedure accurately maintains alpha levels at their intended values as long as statistical model assumptions are met. That means it has to be normality should be there, homogeneity should be there, and independence should be there. If these 3 conditions satisfy, this is one of the good alternative for the multiple comparison. The Tukey's HSD was designed for a situation with equal sample size per group, but that can be adapted to unequal sample size as well. So for that, I'll use that. This is not the only function for Tukey HSD, but for this context I am going to use this function HSD.test. Alternatively, you have Tukey HSD, another function. So but I am using this function from Agricoli package, and the same manner, just keep the parity with other test. That console equals to true, model equals to true, only the function name would be different, but pass by values are same. It will give the same results. And if you just see the last table, that all 4 letters are distinct, there is no common between these among them, so they are all statistically significant. So all the pair comparisons are statistically significant. The last test that I am going to talk about, the Duncan test. This test is adopted from Newman-Kuhl's method. Duncan's test does not control family-wise error rate at the specified alpha level. It has more power than the other post-test, but only problem is it does not control the error rate properly. Duncan's procedure is only very slightly more conservative than LSD. The same pass by values, but the function is different, the Duncan.test, and if you pass this, then that will give you the results, and results are same. So there is no common letters between these group entries, so they are statistically significant. All the pairs are statistically significant. So these are the few alternative procedures for pair comparisons, out of which Tukey HSD is one of the most widely used pair comparison that we normally use it, and the most popular and most beautiful test is the Scheffe's test, which is actually when your model is complex and you want to compare different combinations of contrast the treatment contrast, Scheffe's test would be one of the best among all. So few other alternatives are there, you know, students Newman Kale and Walsh Duncan and Dunet test, etc. These functions also available in Agricoli package. I didn't focus on, those are the few I talked about, but if somebody wants, they can do, all has its merits and demerits, but as a whole, for normal testing you can use Tukey HST, and for complex contrast testing, for complex contrast you can take the Scheffe's test. As a whole, in this module we have seen the different type of